This is the 9th video on our series about Lie algebras, and today we're going to start talking about representations and modules of Lie algebras, although these are really one and the same. And this is where we get to the point where I should probably say, after you know the general structure of an algebraic object, you know, how you generally study it after maybe the basics is via its representations, which is essentially how it acts on a vector space. And then this allows us to study all sorts of algebraic structures via the powerful tools of linear algebra. Okay, so let's get into our first definition. So let's suppose that L is a Lie algebra over a field F. Then we'll define a representation of L to be a pair phi v, where v is a vector space over F, and phi is a map from L to GLV. That's going to be all linear transformations from v to itself, and this map must be a Lie algebra homomorphism. So over here on the left, the bracket is simply whatever the bracket is inside of L, whereas over here on the right, inside of the space of linear transformations on V, the bracket is the commutator. Now, furthermore, if phi is an injective Lie algebra homomorphism, we say that this representation is faithful. So let's look at a couple of basic examples. So any matrix Lie algebra is really a faithful representation of the underlying abstract Lie algebra. So often we'll just work with the matrix Lie algebra, but I like to think of it as really abstracted beyond that. And what we're viewing is just, like I said, a representation. So for example, abstract SL2 is generally spanned by vectors which we call E, F, and H. But the standard representation would be to assign E to the matrix 0, 1, 0, 0, F to the matrix 0, 0, 1, 0, and H to this diagonal matrix with 1 and -1 on the diagonal. And then another important representation that you can easily build out of any Lie algebra is called the adjoint representation. And, well, we'll call that homomorphism AD or AD. And we'll define add x inside of GLL by add xy equals the bracket of x with y. So we've dealt with something like this before, and that's when we were working with Lie's theorem and Engel's theorem. And that's because even though we did those theorems before we looked at representations of Lie algebras, often those are saved until after you look at representations of Lie algebras and you use the structure of a representation. Okay, so in some ways, this is like a complicated representation, more complicated than you might want, and that's because the dimension of GLL is the dimension of L squared. And that's just a standard result from linear algebra. Okay, so let's look at a special case of this second type of representation. So now let's look at the adjoint representation of SL2. And so that means we're really going to want to look at matrices of add H, add E, and add F, those adjoint actions. But in order to do that, we need some sort of like assumption or way to think about the vectors within SL2 as column vectors. So let's think that H is represented by this column vector 1, 0, 0. E is 0, 1, 0, and F is 0, 0, 1. That's because SL2 is three-dimensional. Okay, so now let's calculate add H on all of the basis vectors of SL2. This is how you would calculate the matrix of a linear transformation, like from a linear algebra class. So that means we need add HH, we need add H E, and we'll need add HF. But notice add HH is equal to, well, the bracket of H with H, which is 0. That's by the alternating property of the bracket. And then here, add HE will be the bracket of H with E, which is 2E, by the defining properties of SL2. And then likewise here, we get the bracket of H with F, which is minus 2F. But notice that these equations here tell us that add H is represented by a diagonal matrix. And that's because if you attack H, well, you get a scalar multiple of H, the 0th multiple. If you attack E, you get a scalar multiple of E, and likewise for F. So putting these two things together, that tells us in this basis that we've assigned up here, we have add H, or add H, is given by the matrix, which is, like I said, a diagonal matrix, where the first entry on the diagonal is 0, the second is 2, and the third is -2, just by the role that E and F are playing. Okay, so now let's look for add E, and I'll add F for a homework exercise. Okay, so we need add E applied to H, we need add E applied to E, and we need add E applied to F. So note, this is going to be the bracket of E with H by the definition here, but this is equal to minus 2E. That's by the anti-symmetric property of the bracket. And then here, this will be the bracket of E with itself, which is 0. And then here we get the bracket of E with F, which is H, by the defining properties of the bracket of SL2. Okay, so again, we can read these equations into a matrix in this basis up here, and it goes something like this. So we'll have add E looks like the following matrix. So since it takes H to 2E, we'll have our first column of 0, -2, 0, and I should say minus 2E. And that's because E is given by this vector 0, 1, 0. Then our second column will be all zeros. That's what we read off from this second line. And then the third column will be 1, 0, 0, and that's because H has this vector 1, 0, 0 here. So there's our matrix for add E. And like I said, I'll let you maybe for a homework exercise determine what the 3x3 matrix is for add F. Okay, nice. So now let's move on. So for our next example, we'll recall something called the Heisenberg Le Algebra. This is like an infinite dimensional Heisenberg Le Algebra. We'll take this to be the span of these vectors, which I'll denote by A sub n, union another vector which we'll call K. And the bracket relations go like this. If you take the bracket of AM with AN, you get M delta M plus N 0 times the vector K. So, well, what is this doing right here? Well, this is 0 if and only if M plus N is equal to 0. Or that's non-zero if and only if M plus N is non-zero. In that case, it's equal to 1. Then K is in the center, so it commutes with everything. And now, well, we want to figure out what our representation is. So we'll take our representation to be the following. So it'll be an ordered pair, phi, and then the vector space here will be the set of polynomials, and I'll call those polynomials taking coefficients from C, complex numbers, and we'll have infinitely many variables. So C1, C2, and so on and so forth. And how are we going to define this? Well, let's take phi, well, it's got to be a map from H hat into GL, and then C, X1, X2, so on and so forth. In other words, it needs to take an element of H hat and assign it to a linear transformation on the space of polynomials. So here's how we'll do it. We'll say that phi of A naught is just equal to multiplication by some number lambda, which is inside of C. So it's that linear transformation. And then we'll say that phi of an is equal to n times the partial with respect to n in the case that n is bigger than or equal to 0. And I should say not bigger than or equal to 0, but strictly bigger than 0. And then finally, or not finally, we need phi of a sub minus n to be equal to just multiplication by x sub n. And again, that is also in the case when n is bigger than 0. And then finally, phi of k is equal to multiplication by a number 1. Okay, nice. So that'll be how we define this. And then, of course, we need to check that this is indeed a Lie algebra homomorphism, but that's actually not too hard to do. So let's maybe focus on this right here. So if we've got phi of am with an, so we need to look at cases where m and n are both positive and negative. Let's say that this is the case when m is positive, so bigger than 0, and maybe n is also positive. So that means here we get m, and then the partial with respect to xm, n, the partial with respect to xn. So that's going to turn into m times n, and then we'll have the second partial with respect to xm and then xn minus the second partial with respect to xn and xm. And that's simply by the definition of the commutator here and the way that the partials combine. But since this is acting on the algebra of polynomials where everything is smooth, we know that the order of partial derivatives doesn't matter, which makes this kind of combination always equal to 0, which we should expect because if m and n are both positive, then they cannot sum to 0. Okay, great. And so now let's suppose we have the bracket of phi of am with phi of a minus n, where again m and n are both positive, but now we've got that negative subscript there. Okay, so in this case, we'll have m and then the partial with respect to xm and then just simply multiplication by xn. So that's going to give us, let's see, m times the partial with respect to xm times xn minus m times xn times the partial with respect to xm. Great. But now let's notice that if m and n are not the same, then this is simply 0 again because xn is a constant with respect to the partial with respect to xm, so we can just bring it out front, but then everything cancels. But then if m and n are equal, then by the product rule, maybe keeping in mind that in order to really see what's going on here, and I urge you to do this, you might want to put a test function right here just so it's a little clearer. What we'll end up getting is, which is m times phi of k, which, well, that's exactly what we needed to show to have a homomorphism in this case. And just like to be careful here, this is only in the case when m is equal to n. We get 0 otherwise. But like I said, that's exactly replicating this commutation relation in our setting over there. And then, well, there are a couple of other bracket relations to check that this is a Lie algebra homomorphism, but I'll let you guys do that. And then maybe before we leave this example, I'd like to just mention that this is the so-called Fock representation of this Heisenberg Le Algebra, which is a really important representation inside of quantum mechanics. Okay, so let's move on. Now we're going to look at another definition, which is essentially the same thing as that of a Lie algebra representation, and that is a Lie algebra module. So depending on exactly what you're trying to do, you might work with a representation of an algebraic structure or a module of an algebraic structure. But these are really the same idea. Okay, so let's look at our definition. So given a Lie algebra L over a field F, an L module is a vector space V over the same field together with a map from L cross V to V. And here we'll take the ordered pair xv and send it to x dot v. And this map satisfies the following rules. So we've got this kind of distributive rule of elements of the Lie algebra over the vector space. We've got another distributive rule for elements of the vector space over here. And then furthermore, we've got this bracket rule that says that the bracket of xy acting on v, that's how we say this dot, it's acting on, is equal to x acting on y acting on v minus y acting on x acting on v. So if you look at this, this makes, well, all elements of the Lie algebra look like they are linear transformations of the vector space, and that's exactly what's going on here. But not only are they linear transformations of the vector space, but the bracket is somehow working nicely with this action. Okay, so just to reiterate, a module is a way for an algebraic structure to act on a vector space without going through all of the business of defining some sort of algebra homomorphism. Okay, so here's our theorem which ties these two things together. And that is the notions of a Lie algebra representation and a Lie algebra module are equivalent. So that means if we start with the Lie algebra homomorphism, we can create a unique, kind of obvious Lie algebra module and vice versa. So let's do that. So let's suppose that phi v is a Lie algebra representation. And let's maybe take this representation and create the obvious corresponding Lie algebra module. And we're going to do that like the following, with the following action. So let's define x dot v is equal to phi of x acting on v. So let's recall that phi of x is inside of GLV, just given the fact that we've got a Lie algebra representation here. And maybe furthermore, that means it can maybe obviously act on elements of v via the fact that over here we've got a linear transformation of v, assigned to any element of the Lie algebra, I should say. Now what we have to check is that this action here satisfies these properties that we defined over here. So let's look at that. So we'll have alpha x plus beta y acting on v. So that's going to be equal to phi of alpha x plus beta y, maybe applied to v. We're careful to note that here we don't have a dot. That's because this is application of a linear transformation, whereas this is maybe our abstracted action. Okay, so now given the fact that phi is a homomorphism, we can write this as phi of, or alpha of phi x plus beta of phi y acting on v. But then by the way that linear transformations of vector spaces interact with the vector spaces themselves, we can quickly take this to alpha and then phi xv plus beta phi yv, applied to v in each case, I should say. But then, you know, using this definition in reverse, that gives us alpha of x dot v, or x acting on v, and then beta of y acting on v. So that's the first property. And now let's check the second property. So let's see, let's put a dot here for the first, and we've got a dot down here for the second. So we need to look at what? X acting on alpha v plus beta w. But notice that's going to be phi of x applied to alpha v plus beta w. But since phi of x is a linear transformation, we know we can split up linear combinations in the obvious way. So this quickly turns into alpha of phi of x applied to v plus beta scalar multiplied into phi of x applied to w. But then this is equal to alpha of x dot v plus beta of x dot w. Okay, nice. And now let's look at the last property. So in that case, we need to look at the bracket of x with y applied to v, or acting on v, I should say. So that's going to be phi of the bracket of x with y applied to v. But since phi is a Lie algebra homomorphism, that gives us the bracket of phi of x with phi of y applied to v, which is phi of x times phi of y minus phi of y times phi of x, all applied to v. But then pulling that back via the way we're defining our action, that gives us exactly what we want. So x dot y dot v minus y dot x dot v as needed. So there we did it. We started with a Lie algebra representation and we created an obvious Lie algebra module structure. And now to go in the reverse direction, you would essentially just do this backwards. So let's maybe write the first step right here, and then the rest will be a homework exercise. So let's say that V is an L module. That's what we're assuming. And then we'll define the map phi as follows. So phi of x applied to v is equal to x dot v. We're defining phi by the linear transformation that we get assigned to a Lie algebra element. Notice that just this in reverse, but that's really all you have to do. It's just now we are assuming these properties, and what you have to show is that phi is itself a Lie algebra homomorphism. And then, like I said, I'll leave that as a homework exercise. Okay, let's move on. Now we want to look at sub-objects within the world of modules, and you could push this to sub-representations as well, although I think it's a little bit better to think of them as submodules. It's cleaner. Okay, so let's suppose that V is an L module and W is a vector subspace of V. Then W is called a submodule if, well, it's going to be X invariant for all elements X of the Lie algebra L. So in other words, for all W in W and X in L, X dot W is inside of W. So we like to think of this as follows. So we've got this picture of our vector space V, and then our subspace W. So if you take an element X from the Lie algebra and you apply it to anything inside of W, you land back inside of W. Okay, so now in this case, and by this case I mean when you have a submodule, then the quotient V mod W as like a quotient vector space is a quotient module. And here the action is X acting on the coset V plus W is equal to X acting on V plus W. And now let's just check that this notion of a quotient module is well defined. So let's suppose that V1 plus W is equal to V2 plus W. So in other words, we've got two elements, or really it's one element of the quotient vector space with perhaps two different names. We've got two different representations. And so what we want to show is that the action by any Lie algebra element will take, well, each of these named cosets to the same place. So in other words, we want X dot V1 plus W to be the same thing as X dot V2 plus W. So that would make it work. Okay, great. So now by coset equality, we know that these two cosets are equal if and only if V1 minus V2 is an element of W. So that's something that you most definitely learned in a standard abstract algebra class. You might have seen it with quotient groups or with quotient rings. With quotient groups, it's slightly different because the group operation could not be addition. Okay, great. But notice what this tells us is that v1 minus v2 is equal to something that I'll call little w with little w inside of big W, like that. Okay, great. But now we can write v1 as v2 plus w. But now we're pretty much ready to go. So let's take x and we'll dot it with v1 plus w, our coset. But then by definition, that's going to be the action of x with v1 plus w, so that coset right there. But then this is going to be x dot v2 plus little w plus w. But then by rules of the action of a module, that's going to be x dot v2 plus x dot w plus w. So like that. But then since x dot w is inside of w because we have a submodule, that means that we can just pull this inside of the subspace w, again by coset equality. So that gives us x dot v2 plus w, which is equal to x dot the coset v2 plus w. But check it out, that's exactly what we needed to show to have this be a well-defined action. Okay, let's look at an example. Okay, so for our example, we'll take the Lie algebra of upper triangular matrices, well, 3 by 3 matrices with entries in the complex numbers, and we'll take our module simply to be C3. In other words, the three-dimensional complex vector space. And the action here is clear. It's just simply multiplication by this matrix. And now let's look at a first vector subspace, which I'll call U, and it'll be everything of the form, maybe I'll say B, 0, 0, where B is a complex number. So in other words, it's the span of a single vector 1, 0, 0. And now let's notice that if we take any element of L, which I'll just write as A1, A2, A3, 0, A4, A5, 0, 0, A6, and we multiply it into any element of U, which is of the form B0, 0, well, what do we get? Well, it's pretty easy to see that we get A1B0, 0, which in turn is inside of U. So we took any element inside of U, we attacked it with an element of the Lie algebra, and we ended up with something in U. That's exactly what we need to have a submodule. So that means that U is a submodule of V. Now let's look at another example. So let's take W to be all the vectors of the form BC0, where B and C are complex numbers. So it's going to be the span of E1 and E2 if you want to use that notation. But now we can play the same sort of game. So let's bring this matrix down and let's see what it does to an arbitrary element of W. So we've got BC0 there. So let's see, in the upper entry, just by the definition of matrix multiplication, we'll have A1B plus A2C. And then in the second entry, we'll have A4C0. But really, the defining property of W is it has a 0 down here in the last entry. Well, we still have a 0 in the last entry. So this is, in fact, inside of W, making W, again, a submodule. And then likewise, in both of these cases, you could find out the corresponding quotient module, but I'll leave that to you. And then we'll end with some exercises. Here are 4 nice exercises based on what we just looked at. So the first is to look at the other direction of that theorem that says that modules and representations are equivalent. So let's say we've got an L module V. Let's define a map phi from L to GLV by phi of x acting on V is equal to x dot V. And then show that phi V is a representation. Now, I've cheated a little bit here because we don't know immediately that this map produces a linear transformation on V. But you'll check that and you'll see that pretty quickly, meaning that GLV really is the codomain if you define this V as follows. Then next, let's set L equal to the Lie algebra of strictly upper triangular 3x3 matrices and find the matrix of the adjoint map of an arbitrary element in an obvious basis of L. So I'll let you think about how to do that. Look at our first example where we found the matrix for the adjoint map for all of the elements of SL2. Next, let's find a three-dimensional representation of the unique two-dimensional non-abelian Lie algebra. So I'll let you look up what this two-dimensional non-abelian Lie algebra is. We did that in a previous video though. And then finally, let's consider L as a module over itself via the adjoint action. That is, x dot y is equal to the bracket of x with y. And then show that I is a submodule if and only if I is an ideal. So over here on this side, we're thinking about it in terms of module words, whereas over there, we're thinking about it in terms of the Lie algebra itself. And that's a good place to stop.